A gyrator design with op-amp is shown. A gyrator is a circuit in which symbolically is shown this way, and it has this weird behavior in the sense that the current I1 is not related to V1. Actually, current I1 is with this direction is defined with V2 divided by internal parameter R, and then current I2 is not defined by V2. It's actually, as you can see here, current I2 is actually defined by V at the port 1 divided by internal parameter R. This is what we refer to as gyrator, and a practical implementation of that is shown here using two op-amps as an active circuit. Okay, let's see why in this circuit with this connection we have this interesting relationship between the current and voltages of the two ports shown here. One side note, we make the assumption that the two op-amps are properly biased, so the not shown here, but the supply voltage for the op-amps are properly connected so that and selected so that the op-amps are operating in linear region of operation. And in this case, we make the assumption that the negative feedback is more powerful than the positive, which is the case. Therefore, these op-amps are not saturated and are operating in linear region of operation. With that in mind, let's see what's going on here. So in this op-amp on the right-hand side, knowing that op-amp is operating in linear region, not saturated, virtual short holds. So I'm going to say op-amps assumed to be in linear region. Okay, because of that, we conclude that virtual short should be in place. And that indicates that I should have the voltage at the positive terminal of op-amp should be equal to voltage at the negative terminal, input terminal of op-amp, the same thing. So if I have V1 at the positive input terminal of this op-amp, I should have V1 at the negative input terminal as well. Well, the nice thing is if this node is V1, therefore I can decide what this current that is going through R1 is. That current is simply V1 over R. And since nothing can flow through the input terminal of ideal op-amp because it has infinite impedance, therefore that same current going through R should go through this R as well. So this current is also V1 over R. As a result, we get the fact that therefore this voltage here should be 2 times V1. That's the only way we can get 2 times V1 divided by 2R in series, the same current that we have. So that current goes through these two resistors in series and generate 2 times V1 at this point. Now, remember that the voltage at positive input terminal for this op-amp is V1. Now we have 2V1 here as well. So as a result, we can say that the current that is going this way is 2V1 divided by V1, 2V1 minus V1 divided by R. So it's going to be exactly V1 over R. Okay, so this V1 over R comes through this resistor. At the same time, I1 with this direction is going out of this node toward the input terminal number 1. So therefore, at this node, I can write a KCL and say that the current going through this resistor plus the current going through here, which is I1, because nothing can go through the positive input terminal of op-amp because it has infinite impedance, it's ideal. So I1 plus this current should be equal to V1 over R. So let's write it. So I'm going to write KCL at node, say, let's name this node as node 1. At node 1 is indicating that the V1 minus V2, so V1 minus V2, that is the voltage drop across this resistor R. So V1 minus V2 divided by R should be equal to, we should add to that the current I1. So V1 minus V2 is the current that is going toward left. I1 is the current that is going toward right. So I'm going to add I1. And this sum should be equal to V1 over R that is coming in. So V1 over R. Okay, you can see that V1 over R is cancelled out from the right-hand side and left-hand side, and what we get from this is exactly what we wanted. We get that V2, we get that I2, we get that, sorry, I1 is equal to, I1 is equal to V2 over R by moving this negative V2 over R to the other side. So V2 over R. R is the value of this resistor that is, as you can see, repeated 7 times. 1, 2, 3, 4, 5, 6, 7. So there you go. The current with this direction at input terminal 1, input port 1, is defined by V2 actually, not by V1. Okay, so that's one equation for the gyrator we wanted. Let's check the second one. So remember, this current that is going inward from right to left toward the second op amp, it cannot go through the input impedance of our input negative terminal of op amp because it has infinite impedance. So that current can only flow through upward through this register. Through this resistor. And then we can find the voltage drop across that as well. So V1, the voltage dropped across R is V1 minus V2, and we can just obtain that what the voltage at this point, which is this voltage, gonna be. Obviously that voltage is going to be, so let's say this is Vx here. So I'm going to write that Vx is simply V2 minus this current times R. So R times, and that current, as you can see, is simply V1 minus V2 divided by R. So V1 minus V2 divided by R. Okay, simplify this whole thing, we get Vx is equal to 2V2 minus V1. Nice. Okay, keep this, and let's make sure we keep this. Okay, now let's write the last step. This is V2 that at the input port number 2, and then we have V2 here. So I can define this current, which is V2 over R. And look at the I2. I2 is flowing this way from right to left. So the current that is coming through this resistor is simply this current here, which is V2 over R, because it's voltage V2 across this resistor divided by R. So V2 over R, and then minus I2 give me this current. So let's say this current, I name it as Ix. So I name this current as Ix. Let's just write what we're gonna get. So I'm gonna say Vx at the same time is equal to, obviously, V2 plus Ix times R. So V2 plus Ix times R, but I'm going to substitute for Ix, knowing that Ix is simply V2 times R minus I2 by looking at a KCL here. Okay, so what is the conclusion here? Well, simplify this, and remember, I'm just rewriting Vx. So I'm getting this, this outcome, 2 times V2 minus R times I2. Very interesting. So name this equation B, and we also have this A. Compare A and B because A is defining Vx as 2V2 minus V1, and B actually defines Vx as 2V2 minus Ri2. So by combining these two, we obviously understand that V1 should be equal to Ri2. And hence, we get the second gyrator equation that we wanted. So we get that I2 we get that I2 should be equal to V1 over R, divide by R. That's exactly the gyrator, the second gyrator equation we wanted. So you can see that we managed to realize a gyrator using 2 op amps and this simple circuit. And by gyrator, I mean the interesting behavior or relationship in which that the current in the for the first terminal is defined by the voltage of the second terminal. The current of the first port is defined by the voltage of the second port and vice versa. I hope that this is helpful. In future videos, I'll show other ways of implementing the gyrator using op-amp structure.